So now we have Kostyantyn Vorobyov with a cross-platform framework for the overhead monitoring of programs.
Thank you. Can you hear me in the right? Is it working?
Switch there.
Can you hear me now? All right. So, but sometimes I tend to speak not as loud as I'm supposed to. So if you can't hear me, please tell me to speak up. And also, please free to ask questions during the talk or if you don't understand something. So yes, my name is Kostyantyn Vorobyov. I'm from Bond University, that's in the Gold Coast. And I'm working in the area of program analysis, dynamic analysis in particular. My supervisors are Phil Stokes and Dr. Betty Krishnan. So Phil Stokes is actually here. So if you find some fundamental errors in my framework, you know who addressed. Okay, so I will start with a little bit of overview of the talk. So in the last 2.5 years, we've been working on a number of techniques for detection of errors at runtime. So we generally see how programs execute and try to find errors automatically. So overall, we've decided to put all that into a generic framework where we can define a neighbor and framework at the abstract level and then just derive our analysis from it. So what I'll talk about today is, first I'll give you some background details and of what the monitoring is and generally how can we go about it. Then I'll discuss a little bit what is the current state of events in monitoring and why we're doing this. I mean, taking into account that so many things have been previously done. Then, as I said, I'll talk a little bit of how we can reason about monitoring at the abstract level, and then using this abstract representation, derive something concrete which we can run and see the results. And this is not just an abstract approach, we have implemented it. And we've ran it on a number of programs and found really interesting results. So we actually found real errors in software. Yeah, so at the end of the talk, I'll talk a little bit of our experimentation, of our results, of the errors that we found, of runtime characteristics. And as usual, I'll draw some conclusions. Okay, let's start with monitoring and overall program analysis. So in general, programs can be checked differently. So they can be checked statically or dynamically. When we say that programs are checked statically, we mean that we're just looking at the program automatically or manually and trying to determine whether it has some errors. So the simplest, we're not running the program. This is the key point. So the simplest way is just to look at the program and to do a code review, just trying to see whether it has errors. When we're talking about dynamic analysis of programs, it means that we want to actually run the program and see how it executes and whether it behaves as we expect or in some unexpected fashion. Well, monitoring observes the execution of programs as they execute. So as a very simple example, let's say we have a small utility which converts decimal numbers into binary. Then monitoring would be simply looking for the output that the program produces. So if it produces zeros and ones, then everything's fine. If it outputs something else, then it's some error is in a program because it shouldn't be producing that result. So in some respect, monitoring is actually similar to testing, where we look how programs behave and then can see whether there are errors during runs or they weren't errors. So what is monitoring using instrumentation? When we're talking about monitoring using instrumentation, it means that we're not just looking how the program executes. We're trying to do this in automatic fashion. So we'll take a program and insert some statements that at runtime evaluate the program. returning to our example with conversion of decimal numbers into binary, we can, for example, look at every print statement, at its strings that a program outputs, and simply put a simple check which looks at the characters and, for example, dies with a message that errors occurs if in output we have something other than 1 or 0. So what is good thing about such an approach? Well, first, differently to just observing programs, we can hack into programs and see what the internal structures and how can we manipulate them. In some cases, this is very similar to white box testing. So of course it is reliable because at runtime we have everything instantiated, so we know what values are there. When we try to compare this thing to different static analysis, it turns out that this technique is actually much lighter than doing things statically. Because statically, you don't know, you can see variables, but you don't know what values are. So to get really precise, we need to assume that variables can be everything and check every possible behavior. Here, we don't have to do this. Of course, monitoring looks on program runs one at a time. So we need some inputs to run the program, and we can only say that the run of a program is correct if monitoring determined that. But the rest of the behaviors might be flawed. So again, as a simple example of monitoring using instrumentation, let's say we have an original program, we have some print statement which prints a string. So our goal with monitoring and instrumentation is to instrument a program or simply put statements that observe execution. So what can we do is we can insert a couple of function calls to observe our print statement. So we can put a call called monitoring pre, which uses the same argument as the print function itself. It executes before the actual print statement and it observes it. So for example, if we're checking for something that the program outputs, monitoring can look whether the string foo is okay for a program and either allow the execution to proceed or stop the program. Similarly, we observe it after the execution. So once we've printed something, we can say, okay, this is what the program printed. Was it okay? So monitor pre and monitor post need to implement some features that do the checking. And these features depend on what do we want from the program, what do we want from monitor. So what the actual problem is with all that, that's problems actually. So the first thing is that in that example with pseudocode, you can see that these calls and statements that we put there, they are in the same language that the program itself. And this is the case in many monitoring approaches these days, where somebody who wants to observe programs and instrument programs with statements that observe programs use the same implementation language as the original program itself. Which means that if you want to check a different program in a different language, you need to completely re-implement monitoring functionality. And we don't always want to do that because sometimes we want to look for same properties and reuse this monitoring over and over again. Of course, it is hard to specify because many languages, especially sort of lower-ish languages like C, it takes a lot of time and effort to put these things together. And of course, there is no guarantee that this monitoring will be completely correct. So it is very easy to make error in the monitoring itself, and then which dismisses the whole purpose of monitoring. And finally, we cannot really guarantee that the monitoring program itself and the original program are identical. What it means is that the monitoring, the statements that we put into our program to observe it, change in some way the behavior of the original program. And again, this also dismisses the point of monitoring because we want to monitor the behavior of a program. And if it changes it, then it's a different program we're observing. So how can we address that and how we can solve all these problems? Our solution to that is a generic framework for monitoring of programs using instrumentation. So how do we specify that? So this roughly shows the at the very top level the view of framework. So we'll take two inputs. That would be an original program and the monitoring specification. And monitoring specification is something that tells you how a program needs to be monitored, where do we put the statements, and what is the functionality of these statements. Well, but this monitoring specification is supposed to be abstract. So it doesn't use the same implementation language as the original program, but it's rather translated to it automatically, which also ensures that the original program and the derived monitoring program are equivalent. During the static stage, we'll feed these two inputs to a component which is called the analysis engine. The analysis engine will take a monitoring specification, translate it into an appropriate language, the same language as the original program, derive the statements that we need to insert and the location of points where we need to insert them, and we'll create a monitored program. A monitored program will behave exactly the same way as the original, and additionally it will on the background execute all these little tests. And the overall structure of the monitored program is shown on the right. So it will have monitors. Monitors would be the monitoring functions that run some functionality associated with monitoring. So in the previous example, this monitor pre and monitor post would refer to monitors. Then we have a component which is called the analysis API, this is just a set of helper functions that allow you to specify monitoring easily. And finally, there'll be a component which is called validator, which makes sure that the original program isn't harmed by this monitoring. In such a way, even if you make mistakes in the monitoring specification, the monitored program still behaves in the exact same way as the original. So again, as a part of this solution, we'll make our specification an event-driven specification. Well, we'll take a program and we'll represent it as a sequence of events at the abstract level, rather than going for particular statements. I will talk a little bit about this later. So the benefits of such a solution, again, we could use this abstract monitoring specification across a number of implementations. So for example, we can specify it only once and use for monitoring of C programs or for monitoring of Java programs. This is, of course, if we have this translator which translates the abstract monitoring specification into the actual language. Well, and finally, since we're doing these things automatically, we can make sure that monitoring functionality, that these statements that we include into a program to observe it, do not do anything silly and do not make your monitored program behave differently to the original. So now I'm going to talk about monitoring specification and what parts of the monitoring specification are there. So as I said, we want to represent our program abstractly. And abstractly, we want to represent it as a set of events. So in general, our events would correspond to some syntactic elements of the program, like, for example, assignment statements or function calls. So this A equals B and 3 will be our events. And we can define different events depending on on what you will want from monitoring programs. So note that would be abstractions. So for example, we can have some output types, say assignment and output. What's the benefit of this? The benefit of this is that we can have different assignments. For example, we can have unary plus plus and minus minus operators. Those are assignments too. We can have plus equals, minus equals compiled assignments too. So assignment will be abstraction of all that. So instead of taking every assignment and looking at it at each assignment differently, we'll just specify a class of particular events. And this makes our specification much easier than dealing with every little component. We just don't have to think of it. The translator will do this automatically for us. So, and finally, what we can represent events as functions. Very simple. So, for example, with the assignment where we have a left-hand side and right-hand side, we can represent a function which assigns two values, and let's call it assign, and it takes A and B. Or we can print we can have the output event called print, pretty much exactly the same way we have it at the as the original statement, simply because print foo is already a function call. So, and again, a program here would be represented as a sequence of events. So in here I'll also have some examples. So we'll specify programs as sequences. So here, E1, E2, E3, and E4 are just some abstract events that the program executes. So this program executes E1, then it executes E2, E3, E4, and finally terminates. On top of events, and what can we do with these events? We can specify them as patterns. And the reason why we want to do that is we want to specify some events in the program in some particular order. So we can precisely specify the situations where we want to observe events or where we don't want to observe events. So the event patterns are actually expressions which describe orders of events in the program. Exactly, it's written there. So there can be two different types of patterns. There could be single patterns, or basic patterns, which represent single events. So for example, we can have event pattern E2, and an event matches a program, E0, E1, E2, simply because a program has this event. Also, we can have composite patterns. Composite patterns consist of smaller patterns that are composed using operators. So here, one operator shows the actual operators that we have for the moment. So, for example, we'll have a negation operator not, which would negate an event. So, not event E1 would mean that this matches any event but E1. Then we have a alteration, or we can group events within parentheses. So this is standard. We'll also have two operators, triangle and arrow, which will allow us to create sequences of that. So a triangle operator will allow us to specify a strict sequence of events. So that E1 triangle E2 means that in the program we should have event E1, and it should be immediately followed by event E2. Right arrow specifies non-strict relationship where we can, so E1 appears at any stage before and E2. So for example, this shows a couple of examples. So the first one shows an arrow operator, which is E0 is followed by either E2 or E3. Note that it matches the program 0, 1, 2, 3, because E0 occurred before E3 or E2. So either can be there. The second one, which uses triangle, says that event E0 should be immediately followed by either E2 or E3. This pattern would actually not match the program because E0 is followed immediately by E1. This is what events patterns are, and again, we can use event patterns to specify orders of event in the program and direct our monitoring specification exactly what to observe. And we move to monitoring functions. So monitoring functions, again, returning to the first example, monitor pre, monitor post, are the functions that are executed immediately before or immediately after events, depending on how do we want to observe it. And they use the same arguments as the events themselves. So in that example, we had a monitoring function, monitor pre, which used argument foo. With the same argument the event print was using. But the important, very important thing about monitoring functions is that these functions run in a dedicated memory space. And this memory space does not overlap with the memory space of the original program. What this means is that the state of monitoring does not affect the state of the original program, and vice versa. Which means that errors in the original program do not affect monitoring, and monitoring does not affect original program. So overall, we have them running separately. Well, not actually in parallel, but somewhat similar. Okay, and we finally get to the concept of monitors. Monitor is essentially triple. Monitor consists of an event pattern and two functions. Event pattern tells us which events in the program we want to observe, and monitoring functions specify the actual functionality which should be involved before that event occurs and after that event occurs. So when the monitoring is performed and there is some event, we'll see whether pattern matches. If it does match, we're monitoring function 1. We then allow event to be run, and then we'll run monitoring function 2. Finally, monitoring specification as a whole. Well, so far we've been talking about abstract things. And the question is, how can we represent this here using the actual syntax? So this shows, this code there is how can we do the specification. So we'll take event patterns. We will represent them as regular expressions, where event pattern, the operators that we defined, simply translated one-to-one. So for example, when we're talking about immediate sequence, we'll just put them together, and this will force that event to is immediately preceded. So if it's iter, where it precedes at any stage, we can use dot and an asterisk. So we can specify pattern is preceded by keyword pattern, where a bracketed expression after it actually specifies the pattern itself. Keywords pre and post denote monitoring functions. So there we'll specify code for monitoring functions. And we'll not just specify it using the same language as I said before, but we'll use an abstract language called MSL to specify this monitoring functionality. So afterwards, we can just take this MSL specification and translate it into whatever we need. MSL, by the way, means monitoring specification language, so we decided to be very original about that. Finally, we'll have the analysis API thing, where analysis API is just the set of functions which we can use when writing specification, particularly code over there in pre and post components. And these functions will provide some facilitating functionality. For example, determine whether there is a problem. Normally, this is something a program would not be able to give us, but something that we can generate by running the program. So we'll, additionally to whatever user specifies, we'll include a bit of monitoring that we specify to generate that information. Okay, so overall, we have a monitoring specification in that form, in form of an abstract specification, which is a set of monitors, where monitors are specified using regular expressions, and the MSI. So to get the monitored program, we'll first need to translate the specification in some sort of library in that language, which we can then link against the program. We'll have to further transform the original program to get this additional information, which will help us to create functions from the analysis API, which will facilitate monitoring. And then, of course, we'll need to capture all the events that the program execute and execute all the functionality specified using the monitoring specification to observe this program. Overall, monitoring program will be larger than the original one, of course, and it'll take some extra time to make the observation. This is known as overhead. Okay, so what the transformations are at the abstract level. So the first type of transformation is analysis API. Again, we want to track some parts of the program, in particular, some memory state of the program during the execution. Note that programs usually don't have this information at hand. For example, a program doesn't record, in some sense, the actually addresses that it allocates. It just allocates them. So, but essentially we want to keep track of that. So what we'll do is that we include extra statements that record in memory allocations. And we'll put it into some structure, and finally we'll define some function. We'll just query this structure so we can get this information. So the first series of transformation on the original program would be statements that capture these elements and structure that keeps them, and a set of functional definitions which just can be used in the specification so that we run through the structure and get the information we need. When capturing events, that will be a little bit trickier. So the first thing that we want to do is we want to track what events a program executed. We need the string of events so we can see, we can match patterns that get the string. Remember how we represented a program as a sequence and looked and saw how patterns can be matched? We're doing here the same thing. So we'll have some data structure where it essentially is a string, and we'll represent events as, say, characters. And then having a string of characters and having the string of regular expressions where patterns are translated into regular expressions, we're simply doing a regular expression match. So if the match is achieved, then we can do something. So this function called hOfDate will actually do the tracking of these events. It will do the generation of events that the program executes. So simply we'll take this string of hist and we'll take the event type and append the string with the event. So each time before the event, we'll update our history. The second element is a data structure called mon. What mon does, it records the information from the specification. So mon will consist of triples, where each triple will be a monitoring pattern, an event pattern, which stands for which determines which events need to be monitored, and the names of monitoring functions, such that each time an event is generated, if it is matched against a pattern, then monitoring function is involved. So this is done by using two functions, which is called pre-monitor and post-monitor. So, and they will do pretty much the same thing. So they will take data structure mon, which records functions and patterns. They will hold the history of events and some variable amount of arguments executed by that events accept. So what pre-monitor will do is it will iterate over all the monitors in mon, compare, match them against hist, and run all functions that observe events before their execution. The post-monitor will do the same thing, but it will run functions that observe events after their execution. Note that in our initial example, we just put two functions. And this is different because host monitor invokes all the functions overall, not just one. So it encapsulates it and runs the monitor in a separate memory space where monitors executed by either pre or post monitor cannot affect the program, the original program. Okay, so this shows the actual transformation rules where we will take one statement and create another statement out of it. So it's pretty easy. So on the left-hand side for you, that'd be some event called E, which accepts argument E. And that will write the following. So first we'll run an hupdate function, which will update our history of events. So we'll have our event string up to date. Then we'll run pre-monitor. Pre-monitor will see what events are generated, and it will run the appropriate monitoring functions where Python matches are found. Then we'll run the event itself, and finally, post-monitor will run all the monitoring functionality if heading matches are achieved that were specified using the monitoring specification. Again, a simple example which will demonstrate, and this uses the same event that we used before. So first, we'll declare some history. Then we'll declare monitor structure that captures monitors and buttons, and we'll have some functions called initmon, which initializes it using unspec argument, which stands for monitoring specification. Then we'll run hupdate, then monitor pre, which will run the monitoring functions. Then we'll do the event itself, and finally monitor post will run all the functions which observe event pre after it has been executed. So far, I've been talking about everything at the very abstract level. There are some events, there are some monitoring functions, some monitoring functionality. But when it gets to real analysis, we want to know precisely what properties do we need to address, what are the events, what are the exact functions that form monitoring API, and how to translate this abstract monitoring specification into a complete implementation language. And we will now discuss on how to take this abstract approach and derive a specific analysis which addresses real problems in real programs, and I will show that it redefines useful errors. Okay, dynamic memory allocation. Many people here familiar with this term? Okay, not too many. All right, so we all heard this great lecture today about garbage collectors and how we have much overhead in programs by Steve Blackburn. And he mentioned that there are different ways of doing that. So for example, there is tracing, and then there is reference counting, and that they're coming up with some great things. But he hasn't mentioned a third option, which is, let's just throw this thing away. We don't really need it, right? We can manage memory manually. And this is actually the reason why in this graph that he showed, C and C++, languages that didn't have memory allocation in place, so have it manually, were the best performing programs. And other were performing way, way, way worse. So with dynamic memory allocation, we need to tell the program to allocate memory for us. So in a C programming language, you cannot just allocate a string and hope it to be allocated somewhere in the memory. You can run this magic function called malloc, which does the allocation for you. And of course, after that, you'll need to deallocate it, because we have no garbage collection that cleans up things for us. Another thing that relates to that is that with dynamic memory allocation comes all kinds of memory manipulation operation. We can have absolutely unrestricted access to the memory of the program using pointer. So having a pointer to some memory region, we can dereference it and get the value stored at that address. And we can have pointer arithmetic where we can simply work the memory and do whatever we want. We can assign things to regions where memory wasn't allocated, or do pretty much anything that you can do with a memory at the sort of lower level than normally programs would do. So, and of course, we will have at least two types of errors here. So if we're trying to do something with a memory that hasn't been allocated by the program, we'll get memory errors because that region, for example, is not mapped to real memory. And of course, since we have no garbage collectors, and nobody but us can release the memory that we have allocated, we may eventually run out of memory if we forget to include the statements that actually do the deallocation. So what we want to address in our instantiated framework are the memory safety errors, such as buffer overflows or null pointed references, where these types of errors simply access memory regions that haven't been allocated explicitly by the program. And also we want to address memory leaks. We want to detect is the memory that has been allocated by the program accessible for us, and we can also track how program manages memory, whether we're not trying out of it. Because when you get the program that runs continuously and continuously allocates memory, it will eventually run out of memory, and it will affect any other application running in your machine. And the second type of properties that we want to address are information flow vulnerabilities. Anybody familiar with those ones? Okay. Yeah. So with information flow vulnerabilities is pretty much where we have some information, potentially secret, fed to our program. And when running our program, we want to make sure that this information is not released to some unauthorized parties. As an example, when we're in a Unix system and somebody types in a password, you don't see what the password is. So, for example, if the access is denied, we don't want the program to print access was denied that you and the user password this and this, or the username blah is incorrect. We want it to die quietly, or just say that the username was incorrect. So, but if it prints the password, for example, it's an information flow vulnerability. So we want to be able to check that using our approach as well. So again, initially we were talking about that we need to define all these events to be able to do some checking. So this reflects the actual events at the abstract level of a monitoring specification that we want to support. So it's pretty much straightforward. So we will have events allocant-free, which will allocate and deallocate memory for us. We will have events read and write, where we can read from a memory address or write to a particular memory address. We'll have some event called init and finalize, where init is something that runs before a function starts or a program starts, and finalize is something that is done before a function or program exits. We'll have input and output, which is an abstraction over input and output operations a program performs. And finally, flow would go for information flow, for information from source as copied to from memory address given by source, copied to memory locked at desk. Okay, once we have events defined, so what are the analysis API functions? So again, this shows a little bit of it, just to give you an understanding of what they are. There are many more of them. So we can, for example, have we can have our function to determine whether an address belongs to a program memory allocation, or whether a particular address is initialized. So we can have it initialized, for example, if we just declare a variable and do not assign anything to it. We don't want to use this variable anywhere before we initialize it. Again, we can have the amount of blocks allocated by the program, or the actual the size of a memory block. So we can deduce how much memory the program actually allocates. Is the overall usage by the program. So again, to support information flow, we can have a couple of functions which is called getTag and setTag. So generally, what we'll do in information flow analysis, we'll associate particular memory areas with something called security tags. So for example, some variable which shouldn't be disclosed is assigned a high security level, and then these levels are propagated. So at the end, if we try to output something which is a high level, then this is information flow vulnerability. Otherwise, everything is all right. Finally, we'll have some risk functions like report and abort. Note that abort is the only function which will actually fail the program with some appropriate message. This will alter the behavior of the original program, but in general, it's a good thing to have this so we can stop unsafe executions. Especially this is relevant for information flow analysis. So what can we do at the C level here? How we can map these events. So as I said before, we're looking at abstract events. So we will map them to a number of syntactic elements. So for example, when we talk to memory allocation, we can capture a number of memory allocation API functions like malloc and free, and also capture variable definitions. Now that in our approach, we'll look at everything as a memory block, because variables are memory blocks. Everything is a memory block. Then when read and write events, we'll have some dereferences, array subscripts, assignments, struct subscripts, which is just object accesses like dot in Java, for example. So for input and output operations, we'll take the set of standard functions, such as print and trans, say input and trans. Well, there's quite a few of them in C. When we'll be talking about information flow, where information is assigned from one memory block to another memory block, we'll use all kinds of assignments, and we'll map it also to function calls. Finally, when we'll be instrumenting for init and finalize, which defines the start and the end functions of programs, we'll use scope delimiters. So this end of the function, the curly brace to put something there. Before the last curly brace or return statement, we'll put something there. So the other thing is, how can we actually translate this monitoring specification into the C level? So what we'll do is we will take every monitor in the specification and derive two monitoring functions from it. We'll MSL here, the language that we use to write specification, at the current stage is a subset of the Perl programming language. So the translation there will be pretty much straightforward, where Perl statements are read to C statements. We'll also provide appropriate data structures for built-in Perl data structures like lists and hash tables. We'll implement hist, our history of events, using string, which is optimized as execution proceeds. We will implement triples of monitoring functions and event patterns as simply an event pattern using a C-string and two pointers to functions. So essentially those are two functions names, for example. So in C you can have a pointer to function and then use this pointer to actually execute the functions. Finally, we have all these three magic functions which will do the monitoring for us. The hupdate, which will update hist, and pre-monitor and post-monitor, which will execute functions using function pointers stored in mon. So in terms of enabling monitoring API, is we want to, what we'll do, and what I also mentioned before, is we'll define some data structure. Let's call it T sigma. And this data structure would be updated using some set of statements. For example, we will, after each call to malloc function which allocates memory, or after each function variable definition, we'll put a statement which we call memory. Similarly, when the scope for variables is reached, then we'll remove elements from T sigma. Just as an example, there'll be many other transformations. So finally, we'll provide definitions of functions themselves, so that these functions can be used with monitoring specification, and they will just query T sigma and return some useful results. So, what about implementation? So, what is the point of all this? The point of talking about events and defining this at the abstract level and going through all the motions. This is all to be able to find real errors in real programs. And the best thing about it is we actually build this thing. Build this thing, and this thing happened to be working quite well. So right now, it is built on top of Clang compiler infrastructure. Essentially, we have a compiler which we hacked. So now this compiler produces normal executables, as supposed to, and additionally it takes source C files, transforms them in a fashion that is specified using monitoring specification, which is just an additional argument. And in addition to a normal executable, it creates a modified executable, which will run a little bit longer, but it can prove a program for particular properties. Well, not prove, it can show whether during the run something that we expected happened or vice versa. So right now we're going to talk about a number of experiments that were performed. So the first experiments was...
Sorry, we need to wrap up fairly soon.
Okay, how soon?
We've got about...
I thought I got 15 minutes, at least was the clock. I can do 5 minutes, no worries.
You can go a little bit into the competency time, but yeah, 5 to 10 minutes.
Oh yeah, I'm standing, all right, between the two. Okay, so these 3 experiments, in any case I don't have that many slides left. So we'll have an experiment of memory leaks and show how our prototype is really, really fast and really, really cool, and it really outperforms the existing techniques. And finally, there'll be some user-free analysis where we'll look whether there are some illegal excesses. For example, you've taken some memory block, you've allocated it, then you've deallocated it, and then you're trying to access already deallocated memory. So first in information flow. We took a very narrow problem, and we wanted to see how passwords flow in programs, and whether they are disclosed or not disclosed. We actually found a couple of errors in Unix utilities FTP and sudo. So for example, in FTP, the password in plain text that user gives out is never destroyed. So it is kept in the memory, but when everything is deallocated, and you should know that when free deallocates things, it doesn't override them. So it's like files. You actually delete them, but they're still there, so you can recover them. The same with the password. The password in plain text is still there. And if you're smart enough, you can just take it out there.
In FTP's defense, it is a plain text protocol.
Well, yes, but still. Sudo, which is very widely used thing, it gives out the hashed version, same way. So the good thing that it doesn't give out the plain text, because sudo is very heavily used utility. I mean, and this, the most recent version I'm not talking about some 3 years ago or 10 years ago. So because we address such an error problem, and because we've looked only at the positive flow, we discovered that the overheads are actually very, very low. Well, less than 1% in many cases. So the other experiment was about memory leaks, and what we wanted to do additional to detection is to find where the location of leakage. So not just where the memory that leaked was allocated, but where it is the pointer to that memory was lost. So this shows our memory report. So for example, this reports a memory leak in a tool called Locate, which is used in Linux. Again, the upper part shows where memory was located. This is a stack trace. And this part, it shows where memory was lost and what was the name of the variable that last pointed to that. So essentially, it just can go there and put a free statement, and that will be fixed. So these things are very useful in debugging of that unit. As a nice addition, we discovered that when we do the memory leak monitoring in conventional way, we're way faster than other approaches to do the same. So for example, this shows comparison with Valgrind tool, which looks for memory leaks, and our prototype called Skip. So you can see that green is our runtime overhead, which is on average about 2.5, 3 times. And Valgrind, which averages to 35, around 30 times, because it actually goes higher there. These are SPEC benchmarks, special benchmarks designed for heavy execution. These are used to measure CPU performance. This shows the memory usage, the usage of memory, of how much memory is needed to do the analysis. So again, green is our approach and our memory use, which spikes a little bit over there, but overall it's very, very low. And look how much memory Valgrind uses. Okay, and finally about illegal dereferences and user to free. Again, as we're doing everything at the source level, but not the binary level, we can get very interesting results in terms of debugging. So this shows an error from one of the older versions of Graph. Again, Unix utility, and where you says illegal null pointer, it's actually a source expression that causes dereferences, which causes a program failure. So dereference, so whenever that error is executed, which is a struct accessor, the program fails. So you can see that the expression is sort of big and ugly, and actually it's even more bigger and uglier in the source code. But using that, you can actually pinpoint the exact dereference which causes the error. Plus, of course, it gives the stack trace and where it actually happened. Okay, and we get to the conclusions, where the overall what I wanted to say is that I've here been talking about the framework for monitoring, and that we can indeed develop it at the abstract level and then derive different analysis from it, as our example shows. We've derived specific analysis. And this can be done for any properties that you like, for any events that you like, and you can provide any facilitating functionality for monitoring as well. So there's a very, very wide range of problems which can be addressed by simply deriving things from there. And as it turns out, the great thing about that is that we can take one specification and use it pretty much anywhere, given that the appropriate translators are provided. And finally, we're actually given now the guarantee that even if the monitoring is true, the original program will still behave as expected. It will still be behaving the way it is supposed to behave. And of course, we here have been talking about our implementation, which is really great thing. We're not just developing some theoretical thing. We've shown that this can be implemented. This produces much lower overheads than similar techniques. And finally, we're showing that we've found real errors This can be really useful in practice. So, and on that note, I will finish. Thank you very much for listening. I'm very happy to answer questions, yes.
I think we've got maybe time for one question, two at most. So,
yep.
So my questions were sort of pertaining to a bit more of expanding outside just testing. You're obviously looking for programming errors, but if you started looking for stuff where programs might be exploited from, so you're looking for memory overflows and that sort of stuff.
Yes.
But have you started using it to try and identify vulnerabilities in, Unix applications?
Well, the information flow, which we've done, that's one thing. The other thing that I haven't talked about is we have extension to this information flow. We're looking into input-output sort of thing. So, for example, instead of specifying what passwords are, this is sort of specific. You need to annotate your program. But there we can actually see what comes in the input, and the password will be there.
Yeah.
And then see what the program's output. Because in many cases, you don't have access to the code of application. So it's a web thing, for example.
And so so sort of the next bit there is, have you sort of looked at doing integrity checking on applications as well, like where people were modifying Apache to deliver malware to users? Have you looked at using your software to analyze Apache on that sort of level?
No, we haven't used that software. We haven't used it for integrity checking. But I see no reason why this cannot be done. It can be done, and I don't think that will require much effort.
Okay, one last question. Just probably, does it work with threads? Does it work in concurrent environments and threads?
I have sort of hooks for it in the implementation. It's sort of in testing mode, but I haven't done the testing. So, but we will just need to have this monitoring functions, thread safe, and then everything be fine.
One final question. Is the code available? Can we actually get the code, or is it too late?
Not at the very moment, but generally yes. But it's still, I'm still working on it. I just don't want to give out something that is not completed.
Awesome.
Yeah, but yeah.
Last question. This is just curious. Make sure I understood the implementation correctly.
Can you speak up, please?
This is just me being curious about the implementation.
Yes.
Correct me if I'm wrong. When you actually have a function, you're saying you have post monitoring, monitoring, and post monitoring.
Yes.
Is it where you actually fork the application, then run post monitoring, then run the function, then fork the application again, and then run the post monitoring like that?
No. This is running the same thread, if you're asking that. We can do that, but that will produce the overhead.
That's what I was thinking.
The crazy overhead.
So instead, you're creating your, not creating a...
I'm creating sort of my small environment. I'm allocating memory for myself. I'm allocating a little bit on stack, I'm allocating a little bit of heap, and let functions run there.
But still...
Well, then they return where they need to. They can modify there, they can even have, they won't have any overflows because everything is automatic there. So I'm sure that they just say. Because they are automatic. Yeah.
Oh, so you just copy the part that you need.
Yeah.
Within the same program, in the same thread.
In the same virtual memory space, yes. Yes.
Okay, I think we'll cut it short there. Thank you very much for listening to us.
Thank you.
On behalf of yours, I'd like to give you this gift.